Hi everyone. All right, so today we're entering day 3 of our collision lab practical. All right, so we've already done 2 days of this. So what you did on the first page in day 1 is you guys chose one of the constant velocity cars. You collected some position and time data, or distance and time data, and then you graphed that data. If you do this correctly, you guys should have ended up with a linear line. Now, just talking about a linear line, we know that the slope of a linear line is going to be equal to the rise over the run. Right? And in this case, what's rising is distance, and what's running is time, right? Increasing the y, increasing the x. And if you ever look at a speedometer in a car, you'll notice that the speed is defined as miles per hour or kilometers per second. Another way to say that is it's the distance divided by the time. And that gives you velocity. Okay? So if we're looking for an object that's moving with a constant change in distance, then the slope, or what your m value is going to be the velocity. So that's the main thing that you guys needed from day 1. Now, you also know that if you have a line that looks like this, that it's a linear line. Now, a linear line has the pattern y equals mx. In this particular case, the y is increasing in distance, the m is the slope of your line, right? So this is a number that's unique to each car, right? And the x value is the increase in time. So once you have this model, you guys are able to kind of make some predictions here using that model, right? Just kind of basically plugging your numbers in and doing just some basic math. On day 2, you guys were paired up with one other group, ideally with the opposite color car. What you guys are doing is you guys are asked to, without collecting any more data, to simply share what each group's velocity is. And then, remembering that the whole point of this lab is going to be setting up your cars opposite each other with 4 meters in between. And the whole point is to determine, right, predict where and when the two cars are going to collide. It's a little bit tricky because each car has a different velocity. And that velocity is what you guys are supposed to share with each other. You also want to establish which car is going to start at the 0-meter line and face forward, and which car is going to start at the 4-meter line and face, backwards. Backwards relative, but we're going to start at the 4-meter line and move towards 0. You'll notice that there's another data table here, but this time you guys are going to predict the data, right? Predict where each car is going to be after every second. Now the difference here is you're not collecting the data, you're using the velocity of each car that you found on day 1 to fill out that data table. So once again, you're establishing which car is going to start at 0, which car is going to start at 4. If you do this correctly, one column should be increasing in distance, one column should be decreasing. There is another Desmos graph here. All right, it's different than the first one. This will allow you to graph both velocities for both cars. And then what you'll end up with is you should, if you type in all this data correctly, and you find your line of best fits, you should still find 2 linear patterns. The difference is one should be increasing with time, whereas the other is decreasing with time. The question I have for you guys is, what does it mean when those 2 lines intersect? Yeah. There are 2 methods we're going to use to predict where the cars are going to collide. The first is using your graph, right? You can talk about what does it mean where the 2 lines intersect, right? How reliable is that data? The second piece of evidence is going to be using some math, right? So one thing that we have talked about is we get a linear line or linear pattern for both. However, if you look at your graphs, right, in order to find this correct line of best fit, your line is not starting at 0. Right? At least the distance is not. It's starting at positive 4. So how do we express that mathematically? So again, if you've taken any math class in the last 3 years, you'll remember that we can expand a linear pattern, a linear formula, to include B, right, which is going to be our y-intercept, basically where your line starts. In this case, your y-intercept, or B, is going to represent the starting line for one of the cars. You'll notice that we don't have it for one of the cars. That's not because it doesn't exist, but the reality is, for one of the cars, it's starting at 0. So you could write that in just for consistency, but obviously if you're adding 0 to anything, it's not really necessary to show that. So what we're doing, right, when we say a math model, right, it's taking it out of this mathematical placeholders, right, like y and x and m, and we're actually replacing it with what those variables actually are. So in this case, right, our y, right, our change in y is our distance. That's what we're measuring. Our m is the slope of your line, and that's going to be unique to each of you guys. I'm just using some simple numbers here as a representation. Our x, right, is our independent variable. This is going to be a change in time. And then our y-intercept is where each car is physically starting at the beginning of this experiment. So the goal here is to create a claim, right, using all your knowledge, the graph and some math, which we'll go over here in a sec. Your claim is going to be, where are they going to collide, right, at what distance, right, starting at 0, right, and moving along the line, right, where's it going to collide? You know it has to be a number between 0 and 4 meters. If it's more than 4 meters, or you get a negative number, you probably did something wrong. What's the collision time? Again, you want to think realistically. If you're getting something like 10 seconds, 20 seconds, or like less than 1 second, probably did something wrong, right? You know these cars, some are pretty quick, but none of them are like going to travel 4 meters in 1 second, right? So to create our claim, right, even though it's first, we kind of will develop our evidence and then come back to our claim. We're going to use 2 pieces of evidence, right? Our first one is our Desmos graph. Our second one is going to be using some math, all right? I know I put 3 methods in here, but the third method actually didn't really work out very well. So you have to use math. And basically our reasoning is going to be showing that, right, somewhere. And you can decide how you want to show it. If you're doing the math, you can always do it on the whiteboard and just take a picture and insert it. So here's how we can solve this mathematically. Right. So you have your 2 equations, one for each group. Keep in mind that one has a slope that is positive and a y-intercept of 0, which I'm omitting here just because it doesn't really matter. One group who's starting at the 4 meter line actually has a negative slope, right? That doesn't mean that their car is moving in reverse or that their car is slowing down. It just means that it's moving in the negative direction, right? Starting at 4 and it's moving towards 0. Its distance is decreasing. So one thing that we can do here is we don't know at what distance they're going to collide. We also don't know at what time they're going to collide. What we do know is that they are going to collide at the same distance, right? The red car is not going to crash at the 1 meter line, and the blue car is going to crash at the 3 meter line, right? That's not how crashes work. Cars crash at the same distance and at the same time. So what we can do is we can either set the distance equal in both of these equations or set the time equal in both of these equations. Now this gets a little bit mathy. Again, there's a lot of ways that this can go wrong. So I'm going to walk through one example here using my example slopes. And at the end, you guys can try it on your own, although I would encourage you to try it on your own first. You can pause this video at any point and then try it and then come back. The nice thing about physics is anytime that we are deriving a number, right, like we're trying to solve an answer and our answer will be in the form of a number that's supposed to represent something in the real world. Those numbers should make sense, right? Like I said, wherever the distance is going to be, it should be somewhere between 0 and 4, right? It can't be outside of that. That wouldn't make sense. All right, so we're going to do some substitution. All right, these are just practicing some of our algebra skills. So here's something that we can do that's kind of already set up for us. you'll notice in equation 1, all right, this is kind of our, in my example, this is the red car's information. We actually already have an equation for distance, right? Distance equals this. Because both cars are going to crash at the same distance, what I can do is I can plug this formula in for the distance here in equation 2. So what I'm going to end up with is I'm going to end up with 0.25 times time equals negative 0.5 time plus 4. Look at that. Now, to make this really easy, what I can do here is make sure I do my correct PEMDAS, right? So we kind of do reverse PEMDAS when we're solving equations, right, across the equal sign. I'm going to subtract 4 from both sides because, again, I'm trying to get time by itself. So I'm going to end up with 0.25 time minus 4 equals negative 5 time. Now, a beautiful thing here. You might notice that on both sides of the equation, I have time. And I also have a coefficient, right? A number in front of it. Now, right, I can't really do anything, right? I can't simplify 0.5 time minus 4. However, right, this is kind of like saying, 0.25x. What I can do is, because this is positive, right? It's a positive 0.25. I can subtract. I'm going to just erase some of this so it makes sense. All right, I don't have to divide. I'm actually going to subtract negative 0.25 time from both sides. All right, this is like adding 2x minus 1x. Right? So what I end up with here is I end up with negative 4 equals, again, this is lots of room for making some simple mathematical errors, right? I'm going to end up with negative 0.75 times time. Now, again, my goal is to get time by itself. So I can divide both sides by negative 0.75. Notice I have, time is always going to be a positive number. Again, we are not time travelers here. So I'm going to end up with negative 4 divided by negative 0.75. So you already know we're going to get a positive. I'm going to end up with a number of 5.33 seconds, right? Because we're talking about time, equals time. So my cars are going to crash after 5.33 seconds. Now that might seem like a big number to you. So we'll see. We'll plug this in because, again, the key thing that we do know is that our distance has to be between 0 and 4. So now I have an equation for time, and I can plug this back in into either of my equations. Now, obviously, I want to choose whatever one is going to be the least amount of effort. So I'm going to plug it back into equation 1. Right, I now have a number for time. So I can rewrite this down here. Going back to equation 1, substituting in. Right, I have my distance equals 0.25, right? And now for time, I'm going to plug in 5.33 seconds. And now I'm just multiplying it out. And I'm going to get 0.25 times 5.33. 1.3325. I'm just rounding here. Meters. So that should make sense, right? You always want to look at, does that make sense? I know that my red car is slower than the blue car, right? Or the equation 1 car or the equation 2 car. So they shouldn't be meeting right in the middle, right? It's probably going to be somewhere closer to the 0 line. So 1.33 meters should make sense for collision distance. Now, mathematically, I could have started with solving for the distance and then plugged in for time. Doesn't really matter, right? Just do what's easiest. Obviously, you guys can kind of follow the steps I did. Obviously, hopefully, you guys are able to do this on your own. But I make these in part because I'm not there. So do your best. Always ask yourself at the end, when you guys get an answer, does this answer make sense? Work it out with each other. Use the whiteboards, right? Use the calculator. Solve it. And again, whatever you get, whatever answers you get here, right, should be pretty close to exactly what you got in your Desmos graph. That's an easy way to kind of check your answers. So those numbers are essentially the same. Maybe it's like a decimal place off or so, right? Which would be like 1 centimeter. Then you're good. If what you see in your graph is very different than what you solve for mathematically, then you may want to look back at one or both of the ways that you solve that. Right. Let's keep it here real quick. Let me pause. All right. So after that, once you have 2 pieces of evidence, right, your graph and your math reasoning should agree with each other. You can go ahead and meet up with your group, right? You can kind of help them get to where you got. Set up your cars. You can do this in the hallway. You can do it in the classroom. Probably hallway's easier. There are some, where are my cars? There are some metal ramps in the back of the classroom. Again, these cars tend to kind of veer off, right, in one direction or another, right? They don't go super straight. So you can always use these metal ramps to, like, I don't know, help guide your car a little bit. Okay, you just want to be careful with it because you don't want them like rubbing up their wheels up against them, because then that friction will obviously slow down your cars. It's a terrible rectangle. Good. So just something to consider. Or you can just kind of angle them. You know, maybe they're not straight on facing each other. Maybe you kind of angle them a little bit so that they'll eventually collide. Anyways, so all that being said, you guys develop your evidence, right? Show your reasoning you're working out, and then your claim, right, is going to be your distance. There is a physical paper bullseye that has some point values. I'm going to have you guys, right, place that down where you think the collision distance is going to be. Right, I would take a video from up above, right, so not from the side, but like right on top, so you can see exactly where the 2 cars collide and record that point value, right? And then you can finish up with the test your prediction part. Make sure that you've kind of filled out this whole last page here. Again, for the evidence, there's nothing you really need to add here. This is just kind of the doing part. You'll just kind of take a picture if you're working out. Mostly just the math part, right? Show math. Yeah, and then print it out and put it in your binder, and I'll take a look. All right. I will see you guys soon. Good luck.